Hello class. We are going to be starting a new unit, Solutions. Before we start though, I want to ask you a couple questions. So why is it that your parents or your grandparents, when they cook noodles, why is it that they add salt to the water? Now some of you might know the answer or think you know the answer, but it's actually a very common misconception. I'm sure a lot of you heard before that it's to make the water boil faster. I know that's what my mom said to me, but the reality is it's not why we do it. Why do we do it then? Well, it actually causes the water to boil at a higher temperature. Why would we want to do that? Well, it cooks the food faster, so we can cook our pasta, our noodles quicker. Plus, it obviously seasons the noodles. But that is why we add it to water. Another question. I'm sure you've seen it in the winter. City trucks will be around and they'll be spreading out sand. And in that sand is often, well, especially if it's minus 5, minus 10, in that sand is a bunch of salt, right? They're spreading a mixture to help with traction and to help melt the ice. What does the salt do? Why do we add it to our roads? Why do we add it to our sidewalks in certain cities? Well, it's to lower the freezing point of that ice. How can salt increase the boiling point of water and lower the freezing point of ice and make it melt at a lower temperature? That's wild. How does that happen? We will be exploring that at a molecular level in this unit. Today, however, we're just going to focus on, well, what is a solution? Now, solutions, or matter for that matter, you can classify into two different categories. It can either be pure substances, and pure substances are going to be, your elements on the periodic table, or your compounds. And a pure substance is just like one thing. Right? It'd be a giant block of sodium chloride, a giant block of gold. It could be a block of sugar, right? It doesn't necessarily have to be an ionic compound, it can be covalent as well, but it is one thing, element or compound. Or you can have mixtures, different elements mixed together, or perhaps different compounds mixed together. And these mixtures can either be homogeneous, and a homogeneous mixture, what does homo mean again? We've talked about this before. Homo means same, right? So a homogeneous mixture is a mixture that is the same throughout. An example of this would be something like soda, or gasoline, or the air we breathe. The other type of mixture is heterogeneous. A heterogeneous mixture is one that is not the same throughout, right? Hetero means different. Now, things like dirt, blood, milk, these are good examples of heterogeneous mixtures. So again, pure substances are one thing, and it's either element, compound, and mixtures are going to be different elements together or different compounds together, and they can either be the same throughout or they can be different throughout, homogeneous or heterogeneous. Now, the particles in a heterogeneous mixture are not evenly distributed, and individual particles are often distinguishable. Right? This is a key difference here. If you have something that's heterogeneous, you can see that the mixture is not the same throughout. A mixture of salt and pepper, for example. Or if you look at something like milk, the fat is simply just suspended. The fat is homogenized, but it's a suspension of these fat droplets. It's colloid. It's opaque. You cannot see through it. Now, particles in a homogeneous mixture are evenly distributed and cannot be easily distinguishable. For example, sugar or salt dissolved in water. right? We add sugar to water and you dissolve it. Can you see these particles of sugar any longer? Well, the answer is no. So heterogeneous mixtures. They will settle out if they are left to stand, and there's two main types. You can have suspensions, which are very large particles, and these large particles will settle out if you let them stand. We can also filter them out. And lastly, a good example of this would be something like oil and water. If you mix oil and water and you shake it up really well, you'll see that these oil droplets will be suspended throughout the water medium, but if you leave it long enough, what's going to happen? The oil will separate and form a separate layer. Next up is colloids, and these are a mixture of small particles. They have a cloudy or milky appearance. You cannot see through them. And these particles are evenly distributed throughout the dispersion media. Examples can be things like glue, whipped cream, paint gels, emulsions, foams, and aerosols. Homogeneous mixtures are uniform throughout, which means that every part of the material is exactly the same as any other part in terms of appearance and phase. Right? You dissolve sugar in water, well, you can't tell that the sugar that was once solid is dissolved in that liquid. It appears homogeneous. A homogeneous mixture that may be solid, liquid, or gaseous, composed of solvent and solute particles, is termed a solution. And we're going to be exploring all of the different types of solutions, but as you can imagine, what is the most important solvent in our bodies for life? What does the majority of the dissolving? Oh, it's water, right? Water does. So the majority of solutions we will be exploring are going to be aqueous solutions, and aqueous just means dissolved in water. So that will be the most common one we look at, but there are solutions of each of our different phases mixed together, and let's look at some examples of that. Before we do that, let's look at solvent. What is a solvent? When you have a solution, a solvent is simply the thing that is in greater proportion. So if you mixed, salt and water together, you got a ton of water, a little bit of salt. The solvent is the thing that's doing the dissolving. It's the thing in greater proportion. Next up is the solute, and the solute comes from salt. And that is the thing that is being dissolved, usually in a lesser quantity than your solvent. So those two terms are very important to know. So an example could be making lemonade, right? We throw in that lemonade mixture, those solid crystals into a glass, we stir it up, and that solute, those crystals, mainly sugar in this case, will dissolve into the solvent, which is water. What are the different characteristics of a solution? Well, solutions are homogeneous. They look the same throughout. They are stable. The solute will not settle out over time. Both the solute and solvent will pass through a filter when filtered, so you cannot separate them by filtration. Now, solvents and solutes may be gases, liquids, or solids. Again, we're mainly going to be dealing with liquids here, right? Water, but it can be any of the phases. Solutions are considered to be a single phase, even though the components may have been in different phases to begin with, right? Once that salt is dissolved in water, it is now in the aqueous phase, right? It is dissolved in water, it is in the liquid phase. One more thing. So solutions can be separated by heating. If we distill a solution, distillation, we can separate the components, and that is one of the only ways to separate a solution. So For example, let's say I wanted to get back the sugar I dissolved in my water. What I could do is boil off all of the water. What you'll be left with is the sugar. In a more practical application, one place we use this all the time is in, say, oil refineries. When we extract crude oil from the ground, we have a ton of different compounds. And the way we separate those compounds, that solution, is we heat it up and we boil off the different parts. And we collect them. And that's how you get everything from gasoline to thick engine oil. Types of solutions. There are 9 possible combinations between our 3 phases. And let's start with a solid solute dissolving in a liquid solvent. One of the more common situations we will be exploring. You guys all know a ton of examples of this. Things like sugar in water, salt in water, iodine in alcohol. Maybe you're not as familiar with that one. What about a liquid in a liquid? A liquid solute in a liquid solvent. So, Gasoline antifreeze is methanol in water. You could have methanol in ethanol. You could have ethylene glycol in water, engine antifreeze. All of these are examples of liquid-liquid solutions. What about a gas in a liquid? Well, you're all familiar with one. You drink it on occasion. Well, some of you do. I don't. Soda. So carbon dioxide dissolved in water. Carbonated beverages is a great example where under high pressure, low temperature, we dissolve excess CO2 in liquid, and that comes out of solution when we pop the top. Now, solid and solid may be one you're slightly less familiar with, but a lot of our modern world is shaped by it. For example, brass. You may have done this in grade 9, which is making the golden pennies, where you effectively just put a coat of zinc on your penny, then you heat it up, and the copper and the zinc combine to make brass. 14 karat gold. Most of you probably don't realize that gold jewelry you have, you can't get pure gold jewelry for a good reason. Pure gold is very soft and very malleable. It would be a disaster to make jewelry out of that. It would break and bend far too easily. So what they do is they add other metals to it in order to increase its hardness so it doesn't wear away, so it doesn't bend on you. Another one, copper in silver, is sterling silver. And lastly, one of the most important combinations for our world, when we combine iron metal and carbon together, we make steel. These are all alloys, by the way. Alright, liquid in a solid. Very obscure, because there's not many of these, but a great one is mercury in tin or silver. These are amalgams, and this is what they make cavity fillings out of. Gas in a solid. An example could be hydrogen in palladium or pumice stones. Again, quite rare. Another one, there's a lot of poisonous gases dissolved in coal. Would be another good example. How about a solid solute in a gas? This could be things like mothballs in the air, any substance that is normally solid at room temp and sublimes, or just dust particulate matter in the air. Liquid in a gas, this could be gasoline in the air, or it could be water vapor in the air. Gas in a gas, well, we know this: oxygen mixed with nitrogen, mixed with carbon dioxide and a couple other gases. Well, that is our atmosphere. That is the air around you all the time. So those are the 9 different possible categories of solution. So, quick note. A substance is considered soluble if it will dissolve in a specific solvent. And our next couple lessons is going to be exploring, well, what can dissolve in what? And why is it that certain things will dissolve in each other, whereas other things will not? Like, I know you all know salt dissolves in water, but would salt dissolve in, say, gasoline or cooking oil? Would it dissolve? We'll find out the answer in a couple lessons. Next up, a substance is considered insoluble if it does not dissolve in a specific substance. So, in a specific solvent, sorry. And there's many examples of this that we're going to be exploring as well, but we already talked about one today, oil and water. Why is it that they do not mix? So in your booklets that I'm posting on my website, I want you now to do the practice identifying the 9 types of solutions. And starting next lesson, we will be exploring at a molecular level what is going on when we dissolve things. But a couple quick reminders. What is special about water? What is special about water? Why is it that it has such a high boiling point and high freezing point relative to its atomic mass? Because it weighs almost nothing, right? It weighs almost nothing. So what is special about it? Well, it's very polar, right? It has hydrogen bonding between adjacent water molecules, which gives it a very high level of intermolecular forces. And it's this polar nature of water that makes it so good at being a solvent. So keep in mind, water is very polar, right? Those hydrogens, what charge do they take on? Well, they'll be slightly positive. What charge does the oxygen take on? Well, it's going to be slightly negative, right? Those electronegative oxygens hug those electrons closer to them, making them slightly negative. One more thing. Aqueous. You need to know what that means. If you ever see AQ in brackets beside something, that simply just means dissolved in water, right? Aqueous means you are dissolving in water. So what is your solvent? Your solvent is water. So you see AQ, you know your solvent is water. So keep those 2 things in mind as we move into the molecular level when we talk about dissolving and we talk about things like freezing point depression and boiling point elevation. Have a wonderful day.